All right, well, bonjour tout le monde et bienvenue. Welcome online and in person to Concordia University's fourth space. Thanks so much for joining us for Research That Matters, Sustainability, Biodiversity, and Justice in a Time of Ecological Crisis, Day 3. The panel that you're joining us for now will feature presentations and the work of graduate students that are associated with the LEADS program, and I'll let organizers tell you more about it in just a second. But first, just to let you know that we are streaming to YouTube Live from Fourth Space, which is located on unceded Indigenous lands here in Tiohtià:ke, Montreal. Nous reconnaissons la nation Kanien'kehá:ka comme gardienne des terres et des eaux sur lesquelles nous nous réunissons aujourd'hui. And we make this acknowledgement to bring awareness and understanding of the history of Indigenous peoples and their territories that we occupy. So we would like to just briefly say that we will have time for engagement here with the presenters. So if you're joining us via Zoom, in Fourth Space for the first time, online or in person, well, first of all, welcome once again. We put on daily events here to kind of mobilize and exchange the knowledge that's coming out of Concordia University. So if you'd like to jump into the conversation, feel free to do so with a raised hand on Zoom and turn on your video and simply speak. We'll call upon you, or the chat is activated. And if you're in this space, let us know that you'd like to speak by raising your hand, your actual hand, and then we'll get a microphone to you so that folks on Zoom can hear you. Okay, that's it for me. I'll be passing it over to Jim Grant for some official words of welcome. Hi, Jim.
Hi, Anna. As usual, Anna, thank you and Fourth Space for co-partnering with us. And thanks for that great introduction. You make my job very easy. Basically, I'll just say on behalf of Loyola Sustainability Research Center and Loyola College for Diversity and Sustainability, welcome. This is day 3, event 2 of day 3 of our week-long conference. And we have a wonderful panel here, which I'll introduce shortly. Thank you, Anna, also for that territorial acknowledgement. Much of our research in sustainability is about land and place, and so it's really important to do that. For those of you tuning in on Zoom, if you're not from Tiohtià:ke, I encourage you to, investigate the land on where you are situated now. So without further ado, I'm going to pass things over to Odile, who will talk a bit about LEADS and tell you about these great students we're going to hear from. So thanks very much.
Thank you, Jim. So indeed, my name is Odile. I'm the program coordinator of LEADS. And before I leave the floor to the 4 amazing trainees from LEADS, I'll have a brief foreword about LEADS, so what the program is and what does it stand for. So LEADS is a bilingual and inter-university program around the topic of leadership in environmental and digital innovation for sustainability. We have trainees, so students, postdocs, and PhDs across the 4 universities here of Montreal, so from Concordia, McGill, UQAM, and Université de Montréal. And we also have 2 amazing partners, which are Sustainability in the Digital Age and Future Earth. The program seeks to drive a deep transformation in society towards more sustainable and equitable patterns, towards an interdisciplinary approach. So we try to bring together diverse communities from different sectors to foster this deep change in society, being it with the science community, but also on the digital innovators side. The program is clustered around 3 main topics. So we have climate change mitigation and resilience. Then we have advancing systems-based approaches to SDGs. And the third one, enabling transformative power of sustainability in the digital age. For the students, PhDs and postdocs attending the program, they have access to a bunch of activities, including an internship, then a summer school that's usually taking place in May, the development of skills such as collective leadership and digital collective intelligence, and then we also have monthly workshops and international science policy meetings. The team, so we have a lot of people working on this program, and we have professors from the 4 universities mentioned, and we also have 2 partners from Sustainability in the Digital Age. Then last thing I wanted to say before I leave the floor to our panelists is we have a new Instagram page. So if you want to follow us and see our latest activities, upcoming dates, and also if you want to meet the team, see who's in the program, I invite you to follow us on Instagram by using the QR code or just searching Leeds Montreal on Instagram. And then we also have a brand new website. So if you're curious, go ahead. The 4 panelists presenting today are Camilo, then we also have Graham, Fateme, and Antoine. They will respectively present their research and some results from their research. So I'll start with Camilo, who will be presenting his research on current indigenous-led and community-led nature-based solutions and future pathways through AI. Then we'll have Graham presenting his research on modeling impact of wood harvest using machine learning emulation. We'll follow with Fateme on paleofluid reconstruction of the Ottawa River Basin using Oxbow Lake sediments. And lastly, Antoine will be presenting his research on late Holocene paleostorm reconstruction based on XRF scanning and sedimentological data. So without further ado, I'll leave the floor to Camilo.
So thank you so much for having me. I'm a postdoctoral fellow, and my supervisors are Professor Damon Matthews and Professor Liana Ubali-Juro. And I titled my presentation, Current Indigenous and Community-Led Nature-Based Solutions and Future Pathways Through AI. So we know that forests store a lot of carbon, and because of that reason, we think that they are one of the most cost-effective ways for climate change mitigation and, of course, like nature-based solutions. So in fact, we know that maintaining and improving forest management represent 55% of the unrealized carbon storage globally. And also globally, so we know that natural ecosystems are not unoccupied. In fact, a great proportion of natural ecosystems, including forests, they overlapped with the customary lands of indigenous peoples and local communities. And because of that, indigenous peoples and local communities' lands are a potential component of nature-based solutions that aim for climate change mitigation actions. And of course, other values and benefits that might derive from conserving biodiversity, including food security, health, and of course, cultural identity. And so due to this potential role of indigenous people and local communities' lands, among different factors, they have not been exclusively influenced by local worldviews and values, but also by diverse policy interventions, such as declaring protected areas or maybe imposing protected areas. In other cases, providing land rights or providing financial incentives for conservation or protecting carbon. And additionally, these lands have been influenced by different drivers of land use related to market access or agriculture's suitability. So to understand the interplay of all these factors that involved indigenous peoples and local communities, and of course the climate crisis, I have been trying to answer the question, are indigenous peoples and local communities' lands nature-based solutions for climate change? So I'll show you today a couple of case studies about them. Let's start with the first one. So the first case study extended across Panama and the Amazon basin portions of 4 countries where we use carbon density maps, confounders, defined confounders related to market access and agriculture suitability. And after we performed matching analysis and linear mix models to control for these confounders and specifically to determine if indigenous territories, protected areas, and their overlaps, which are like our treatments in this quasi-experiment, actually stored more carbon than other lands that were unprotected, which are like the control. And we did this comparison annually from 2003 to 2016, and that is defined the temporal effect. So overall, what we found is that after controlling for confounders, indigenous territories, as you see on the slide, are effective in conserving carbon stocks across Panama and Amazon basin countries. So there you have Brazil, and you see that areas defined as indigenous territories guaranteed 5.7% more carbon per hectare than more than other lands lacking protection in 2003. And you see that the effect increases in 2016. It almost doubled. And if you check, this effect was actually higher than protected areas, and of course, like the effect of overlapped areas, those that are indigenous territories and protected areas are the same time, was the effect was higher than indigenous territories and protected areas. So that was case one. So let's go to case two. Let's talk about local communities. So I will focus on community forest concessions in Petén, Guatemala, that's Central America. And so these concessions that I defined community managed protected areas represent diverse social groups with varied historical and cultural backgrounds, and they have engaged in REDD+ projects, which basically aim to provide financial incentives for avoided land use emissions. So along with other protected areas, community managed protected areas, in this case, are located in the Maya Biosphere Reserve, which is surrounded by this purple line. And so again, across this region, we define carbon stocks, confounders related with market access and agriculture suitability. And once again, we used a matching analysis and linear mixed models. In this case, first of all, to determine if community managed protected areas avoided more land use emissions than the controls. In this case, other unprotected lands, sustainable use protected areas, and strict protected areas. So that was one of the temporal effects that we explored. And then, similar to the other case, we try to see if community managed protected areas not only avoided more carbon emissions, but also stored more carbon. We checked like the standing carbon relative to other unprotected lands, sustainable use protected areas, and strict protected areas. So this is what we find. So first of all, we found that community managed protected areas resulted in avoided carbon emissions. So let's see what happened before REDD+ incentives. So for example, here you see that community managed protected areas relative to other unprotected lands in the period 2007-2011 avoided around 20 tons of CO2 equivalent per hectare. But then if we see what happens after REDD, after the financial incentives, so we see that there's a reduction in avoided emissions. So maybe it's not working so well, but actually there's a slight increase when we compare community managed protected areas and street protected areas. So there's some limited effectiveness of this incentive here for that period of time. So let's see carbon stocks. So basically what we found is that these community managed protected areas are effective in conserving carbon stocks, and that happened before and after REDD. So for example, if we compared community managed protected areas with other unprotected lands, we see that throughout different years, the amount of carbon stocks were more than 100% higher than other lands. And what it's more surprising is that they even tend to store more carbon than strict protected areas, which are not supposed to allow any extractive activities. But once again, REDD+ is not about compensating for the standing carbon, but it's just about land use emissions, avoided land use emissions. So what can we say about this? That after controlling for confounders, socioeconomic and environmental confounders, that we found that indigenous peoples and local community lands, they bring stability to carbon stocks. So we could say that they are nature-based solutions for climate change. However, as I was mentioning, incentives such as RED, they focus on avoided land use emissions, but there are no mechanisms to reward these stable forest covers, especially forests that have irrecoverable carbon that if lost will not be recovered by the time we want to reach our net zero emission targets. So we could say, of course, that the customary land tenure of indigenous peoples and local communities, of course, driven by their worldviews, they not only contribute to conserving carbon stocks and climate change mitigation, but they contribute to other ecological and social outcomes related to biodiversity, water, food security, and so on. So let's talk about future pathways. So I spoke about carbon, but as I mentioned, there are some missing pieces if you want to talk about nature-based solutions. So how can artificial intelligence help us to reach this, to reach and find effective nature-based solutions? So I'm going to show you just one example here. So, let's just show it all. So this is a case, for example, related with biodiversity. So Silvestro and collaborators have shown a very impressive algorithm that relies on neural networks that uses biodiversity data and then incorporate data regarding anthropogenic disturbances, population density, climate, to identify which areas are cost-effective priorities for biodiversity conservation. And this is even more impressive because this algorithm could follow a reinforced learning process that can update this prioritization approach because of emerging or new anthropogenic or climate disturbances. So this looks like a great opportunity to find potential nature-based solutions. But I think the great challenge here is about how do we leverage artificial intelligence in an equitable way. And so here are some opportunities that we need to explore. So we, of course, need, if we want to prioritize nature-based solutions, we need to perform processes of co-production, involve indigenous peoples and local communities. And of course, take into consideration different contexts of land governance. So of course, it will not, the goals will not be exactly the same if we talk about private lands that do agriculture or indigenous lands. So that needs to be put into consideration too. And we need to, of course, to explore different co-benefits, not only biodiversity, but carbon stocks, as I spoke before, but also water quality, food security, and cultural values. So I'm going to finish with this like graphic summary from Sustainability in the Digital Age that hosts the Canada Hub of Future Earth. And this is part of some workshops that were done 1.5 years ago and are giving us the directions for the current project I'm working at. So if we want to use artificial intelligence to create algorithms to monitor and prioritize nature-based solutions, of course, as it's shown here, we need to involve local communities, we need to involve indigenous peoples. It needs to be a process from the bottom to the top. And so this process can not only be about carbon, biodiversity, and so on, but we also need to integrate other worldviews and values, including cultures, stories, and local wisdom, other worldviews. And of course, if we are creating these equitable nature-based solutions, algorithms, there are other aspects to take into consideration, which is in terms of what are the consequences of automation, ownership, and access for local communities and indigenous peoples. And I guess I will finish with that. Thank you very much.
Thank you, Camilo, for this very interesting nature-centered and community-centered research. I would like to leave the floor to eventual questions, either in person or even online. You can ask questions on Zoom as well. Yes.
Oh, thanks for that really interesting presentation. I'm wondering if you could talk a little bit more about what's driving those significant results. Like, why do we see more carbon storage in a community managed conservation area compared to a different what are the driving variables in there?
Yeah, interesting question. So, so I would say, for example, of course, in the case of indigenous territories, and this is not something that I covered here, but we have explored elsewhere. What we have found is that, of course, this stability of carbon stocks is driven by local values. And just to give you an example, I guess in a spatial way, what we have found is that indigenous people's land use is very stable on time. It does not expand into the forest. So the areas that are used for agriculture today are basically the same areas that were used 20 years ago, 40 years ago. So and of course that is driven, as I'm saying, by local values. So because people, of course, appreciate some land for food security, but then the forest also provide other instrumental and cultural values that are as important as producing food. So that could be one of the reasons. And then just to mention the case of local communities, this case that I showed about community concessions, I find valuable that they have been doing a lot of bridging knowledge processes. So they got involved with NGOs. So they have been very active in interacting with other actors that are, like, I believe, improving their forest governance. That's I guess the two ways that I would exemplify it. Thank you.
Thank you, Camilo. Do we have other questions? Yes, Dana.
So you made a distinction between avoided emissions and standing carbon, and at face value, you would think that those two things would be highly related. Right? If you have fewer avoided emissions, you should have more standing carbon. But you kind of found different relationships, and so I wonder if you can speak to why they might be different, and why like focusing on standing carbon might be a useful complement to the kind of focus on emissions.
Yeah, thank you. So of course, like, if we have more avoided land use emissions, then we are expecting more carbon. But I believe the value here is that, and I guess it's the problem of the current policy incentives, is that they are rewarding for the carbon that was not lost based on some previous baseline. And so, in simple words, in some cases and in some countries, that is basically rewarding those that have been or haven't been doing such a good job in conserving forests. So if, let's say, I'm a local actor, or I'm a country that has been deforesting a lot and lost almost all of my forest, and then I start to receive these compensations, I'm going to receive a lot of financial incentives. But then if I'm a local actor or a country that has been conserving the forest for a long time, and of course the current land use emission, like avoided land use emissions compared with the past, are very small, I'm not going to receive a lot. So I think that's a key problem of the current financial incentives. And of course, if we are talking about a standing carbon, we are not only talking like old standing carbon, we are talking about like forests that have been probably intact or barely disturbed for a long time. So they are the home, of course, of tremendous biodiversity and other benefits that emerge from these ecosystems, compared with a, like, let's say, very disturbed forest or ecosystem. Thank you.
Thank you, Camilo. I think we'll proceed with the presentation of Graham.
Hi, everyone. My name's Graham Klein. I'm a master's student with Damon Matthews. I'm just finishing up my research, and I'm here today to talk about it. I'm working on estimating forest carbon dynamics using climate model emulation. So I just want to talk about some context first, and give a definition to what a climate model is. There's a pretty wide variety of different climate models. Some of them can be pretty simple in replicating the world's climate, and some of them can be pretty complex. All of them are based on mathematical functions and processes to emulate the world's climate. The image I've shared here is a fairly complex climate model, and it represents many different processes. This is the land component of a climate model. So you can see on the micro level, there are different processes represented in root carbon and soil carbon and plant carbon. And on a more macro level, there's processes represented of forest disturbance events like forest fires and wood harvest. So these climate models are often very expensive to run, often ran with supercomputers that are not very accessible and expensive and rare. So to sort of democratize and make this power more accessible, we can use machine learning to approximate the output of these climate models. So that's what I'm trying to do here. And in particular, I'm focusing on modeling one aspect of a climate model, just this land forest carbon aspect. So instead of trying to model the whole or emulate the whole climate model, just picking one aspect. So first of all, it's good to create an accurate estimation of the forest carbon that closely predicts the same predictions that the climate model does, but also I attempt to apply this emulation to a scenario, so to put it into practice and show that it is useful. I apply it to Canada's managed forests. The managed forest is the place where the vast majority of wood harvest occurs in Canada. You can see that it's overlaid with the majority of boreal forest. These southern parts are temperate and arid regions. So first I train the machine learning model with the climate model output. So I teach the machine learning model the different relationships between the variables. And then I take this emulation and apply it to an observed data set. So climate data that is more closely related to our actual climate. And then I take this observed data set and apply it to a reforestation scenario that I developed. So the reforestation data is based on a data set provided by the National Forest Inventory. You can kind of see here, but each little pixel is a different forest or a wood harvest event, and each color is a different wood harvest event year. So it's kind of hard to see, but when you sum it up, it ends up being quite a bit of wood harvest over the past 30 years. So what I did was take this data set and sort of fill in all the holes where there'd been wood harvest and sort of make a scenario that no wood harvest had occurred over the past 30 years. So kind of what Camila was talking about assuming standing carbon as opposed to carbon removed from wood harvest. So then I can kind of see what would have our carbon stocks look like if we hadn't done any wood harvest over the past 30 years. So these are some of the inputs, well, all of the inputs and outputs of the machine learning model. So I don't represent all of the carbon output, but instead I just represent above ground biomass and the first meter of the soil pool. And I chose this just for validation reasons. Several other studies use these metrics and methods as well. So the bottom is the difference between the reforested data set and the observed data set. And then on the right here is the difference between them. So you can kind of see these more yellow parts are where lots of wood harvest has occurred, and therefore lots of tree cover has been replaced in the scenario. And this middle section is the above ground biomass estimation for the simulated reforestation versus the above forest cover. So you can also see the difference, and you can see sort of spatially that it's a little bit different than where the vast majority of tree cover occurred. And again, this is the top part is for soil carbon, and you can see it's more closely aligned with the above ground biomass. So I found this interesting. I thought it would way more closely align with the tree cover than is shown here. And that sort of led me to try and start interpreting what the model was trying to do. So I took a north-south transect of transect that covers Montreal and goes into Quebec a little bit. And I took this transect of the study area and applied a machine learning interpretability algorithm called integrated gradients. And this algorithm approximates the importance of each feature according to the output. So for example, if precipitation has a large impact on soil carbon, it will have a higher attribution. So this is the positive attributions for both above ground biomass on the left and soil carbon on the right for that small transect. This is over a 30-year time series, which was the study time series. And we can see, well, lots of interesting things. The model positively attributes both soil carbon and above ground biomass to low summer temperatures, which is this, and low winter temperatures. So a more cold environment has a stronger signal for capturing carbon. The same sort of signal is seen on the inverse for the negative attribution. You can see, most importantly or interestingly, the soil temperature, which is this row here. For each higher signal, the attribution is lower. So a higher soil temperature attributes to a lower carbon amount. And the same goes for the temperature, the summer temperature here. Yeah, so these results kind of help me gain confidence in what the model is predicting and how and why it's predicting it, because of the results not being so intuitive. So I think there's some things I'd like to really emphasize. This is never a replacement for the process-based modeling that it's depending on. It's sort of like an additional tool or something that can be added along to increase visibility or accessibility. Sort of the methodologically, I could have done much more exploration, or could do in the future, of different machine learning architectures, or a variety of hyperparameters. And the simulation that I developed is sort of, well, it's make-believe in that I sort of took forest trunks and just dropped them in without considering growth dynamics and how that impacts carbon content. So yeah, that's it for me. Thank you.
Thank you, Graham. Do we have any questions?
Hi, nice presentation, Graham, thanks. I wonder if you could talk about how you see the potential for these methods to be applied at a broader scale. Could you, you took your transect sort of Montreal and above, could you apply the same thing to Canada as a whole or more globally, or how would that work?
Yeah, I think that's, well, even in Canada, there's lots of different climates and biomes, so it's hard to get a sort of more general picture of the climate. But I think with more nuanced modeling or emulation, this could be done. I think we see it a lot in language-based models, that there's lots of nuance being applied. And I think if that same sort of care was applied to the climate, it could be just as nuanced.
I think we can go ahead and start with the third presentation. The presentation of Fatima. Sorry, we had another question.
Thank you.
Thanks. Okay, thank you. We'll proceed with the next presentation of Fatima.
Hello, everyone. My name is Fatima Salami. I'm a PhD student in Geography, Urban and Environmental Study at Concordia University, supervised by Dr. Jenny Sanjax and Prof. Matthew Perez at Bishop's University. I'm a lead trainee, and today I'm going to talk about paleoflood reconstruction of the Ottawa River Basin using oxbow-like sediments. Let's have an overview of the content of this presentation. I will have a short introduction, talk about my goals, hypotheses, methodology, and expected outcomes. Let's talk about the problem that my project is focused on. First, the severe floods in 1974, 1976, 2017, and 2019 in the Ottawa River Basin. The floods of 2017 and 2019 led to the evacuation of 14,000 people and governmental costs of $1 billion. The 2019 floods, flood damage in the ORB surpassed that of 2017, which was thought to be the 100-year flood. Since then, there have been concerns about the repeated events of this kind. Therefore, to avoid such expensive damage and better understand if these floods are due to anthropogenic climate change and or land use change, we need better long-term data on flood risk and vulnerability. Here you can see photos of 1974 floods and 2019 floods. Also, unfortunately, the regional flood records are short. You can see here the water survey of Canada hydrometric stations on the main stem of the Ottawa River. The green points are stand for active stations, and the red one, the inactive ones. You can see the actives begin at the base around 1910 here. And there are few stream flow gauges on unregulated basin tributaries. Here you can see the natural active stations in ORB pictured in green. In addition, our data is contaminated by dams. The ORB is heavily dammed. You can see the dams in red shapes here. Therefore, there is not enough data to accurately estimate the natural 100-year flood return period in the sub-basins, but the missing long-term data on the frequency and magnitude of major flooding can be inferred using floodwater sediments that are different from sediments deposited in non-flood conditions. Now, let's look at the causes of flooding in the ORB. The Ottawa River watershed, with a size of 146,300 square kilometer, has 13 main reservoirs that are used for a variety of purposes, including flood reduction. 60% of the watershed, as you can see, is unregulated and without storage capacity during floods. As a result of rain and snow melt over the ORB, the Ottawa River experiences high flows in the spring. There are two different peak flow events in the Ottawa River, usually about 3 weeks apart. The first flood peak originates from unregulated floods from the southern tributaries and is typically the lesser of the two peaks, but with ice present. Flood damage can occur because of the ice jam, and the second peak is I have a problem with this. The second peak is as a result of combination of high flows from the northern tributaries and headwater area, and is partially regulated by reservoirs. Better understanding of the risk and vulnerabilities to flooding on the century scale and longer in the ORB, also reconstructing paleo flood frequencies of the ORB using sediment cores are the goals in this study. Regarding hypotheses, ORB has centuries of active flooding, then centuries of less active flooding, and also we think that in ORB, the floods have increased during the last 2 centuries due to land use change. You can see here a photo of land use in ORB. We have agriculture, industry, residentials. Now here I want to talk about the methodology that we use in this study. I grouped them in 3: fieldwork, lab work, and analysis. For fieldwork, we will examine sites before fieldwork using aerial photographs and Google Earth Engine and Google Earth Pro to find stable oxbow lakes that have existed through the past century. We take sediment cores from oxbow lakes from 3 Ottawa River tributaries, one of them River Rouge that we cored in this winter. We core off a raft in summer or off ice in winter. You can see the research team taking a surface core. We use Google Earth Pro to find the candidate oxbow to core. Also, we use Google Earth Engine images from different seasons to check if our candidate oxbow lake would reattach during higher than average spring floods. Also, we use aerial photos from different years if they were available. This winter we caught a few oxbows on River Rouge. We can see here the places we caught. Here is the basin and the river in dark blue. And here is the River Rouge and the oxbows that we caught. We try to core different places in each oxbow. First, we caught this oxbow and then a few other oxbows. The river is oxbow. We use surface corer and Livingstone corer for coring sediments. The Livingstone corer can be used to collect successive 1 meter drive of lake sediments, which are extruded into split tubes and protected by rafts, as you can see here. Extruding sediment process. Here is what the core looks like using Livingstone. Once back at Paris Lab, the sediment cores will be longitudinally split. I will do carbon 14 and lead to then to date them, and I will construct edge depth models. And for detecting sediment changes, we use different methods, including CDS scan, XRF. For the analysis, the sedimentary data from the cores will be compared to the instrumental flood records over the past century. For example, here the instrumental data show that the annual peak flow is showing a rise over the period of record. Also, the dated flood occurrence will be used to estimate flood frequency of the most recent millennia. And the long flood record will be correlated to proxy reconstructed climate oscillations such as NAO, MAO, ENSO, and drought records from the North American three-ring drought atlas in order to better understand the role of long-term climate drivers of the ORB. Expected outcomes, longer-term perspectives for flood risk reduction planning and to establish flood baseline in the ORB. This flood research will benefit cities, smaller communities, regional watershed managers, and the insurance industry in these areas by providing them with long-term flood baseline. It will seek to answer the question of whether severe floods are increasing in river basin due to anthropogenic climate warming. Thanks for listening.
Thank you, Fatime. Do we have any questions?
Thanks, Fatima. Naive question here. Oxbows don't occur randomly in the landscape, but are they, and yet they're a good measure of flood frequency? Could you just explain that for us?
Yes, thanks for asking. Oxbow lakes act as sediment trap. So how oxbow lakes form is that they were used to be part of the river, but when rivers they change their location, the oxbow detach from the river, and some of the oxbows during the flood they reattach again because of the flood. So the sediments in oxbow lakes, we use oxbow lakes because it's a good place for sediments they are different from the sediments that normally you can find, because when we have floods, the sediments settle down there. So that's why we choose oxbow lakes to core. You're getting.
Any other question? Okay, thanks a lot, Fatima. We'll proceed with the last presentation of this session. We'll go slightly over time if that's okay. We'll have the presentation of Antoine now.
Okay. Well, hi, everyone. Thank you for attending this session hosted by the LEAD program. So my name is Antoine Lachance. I am a PhD student here at Concordia University. And today I will be presenting my work from my master's thesis, which was about reconstructing late Holocene storm on the Magdalene Island from homotrophic peat core. To better understand the relationship between storm and climate over the long term. So of course, this work could not have been done without the support of my two supervisors, Matthew Perez from Bishop University, Janine Marie Saint-Jacques from Concordia, and two collaborators, Pierre Francus from the INRS in Quebec and Nicole Sanderson from Geotop at UQAM. And so just a little bit of background. So tropical cyclones are a ever-present hazards for coastal community in Eastern Canada, especially because we are located in the northern limit of the hurricane track in the North Atlantic. However, it is difficult to predict how tropical cyclones are going to change with future climate change. In part because we don't have long-term data on how tropical cyclones behave over the long term. But one thing that we can expect is that with increasing sea surface temperature, with increasing temperature caused by climate change, we can expect a potential northward movement of the main cyclone track in the North Atlantic, which would expose Eastern Canada to more cyclone in the coming century. And so my research aims at to improve understanding of the climate and storm on the long term by looking at paleoclimate archive, so to go beyond the instrumental record of storm. And this is related to sustainability because we can use these insights to better understand how we'll change with climate change and to better predict and put this data into modeling and therefore predict storm behaviors with increasing climate change. And so the basic concept behind doing paleotempestology is that when a site is impacted by a storm, the strong wind will transport material, either sea spray or aeolian sand, into a more inland area where this material will accumulate. And using an umbrotrophic peat bog is relevant for this kind of study because umbrotrophic peat bog accumulates over a long period of time, and they are isolated from the watershed, from running water, river, and stuff like that. So they receive water and mineral only through atmospheric processes like storm. And so the goal is to take peat core and then to find these storm sediment and to date them, and therefore to reconstruct storm occurrences. So this is my research site on the Magdalene Island, which is located in the middle of the Gulf of St. Lawrence. We have two sites on the southernmost island, which is Île du Havre-Aubert. The first site is Tourbière de l'Anse à la Cabane, which is right here. And this site is closer to the coast, about 250 meters from the coast, so very exposed to storm winds. Our second site was Tourbière du Lac Moncoq, which is a bit more isolated, about 2 kilometers from the closest coast, so a little less exposed to storm. And so I'll do a brief description of my two cores. So the first one, TAC, is about a little more than 3 meters long. So we did dating, radiocarbon dating, and lead-210 dating on the core. And the core is about, in its totality, 5,000 years old. However, the sedimentological and geochemical analysis, which I don't have time to go in detail here, tells us that the core was umbrotrophic, so the section that we can actually use to reconstruct the storm. So it was umbrotrophic in the last 1,000 years, and also between 1670 and 1100 before the Common Era. And TLM was about twice as long. The model was based on 9 radiocarbon dates, no lead-210 for this one, and it is also 5,000 years old. Again, the analysis tells us that the umbrotrophy was present at this site during the last 2,000 years. But because the two cores are umbrotrophic together during the past 1,000 years, we decided for my master's thesis to reconstruct storm only for the past 1,000 years to be able to compare our results. So the first step in doing paleostorm reconstruction, once you have the core, is to select a suitable storm proxy. And so a suitable storm proxy needs to be the highest resolution possible, needs to be abundant in the core and associated to the coarse grain fraction of the sand that would be transported into the peat bog under extreme condition. So we didn't use sand because it was not high resolution enough in our core. So we used titanium, which was measured through microfluorescence, X-ray microfluorescence, XRF. So that was at the millimeter scale. And once we have the titanium count in the core plotted by depth or by age, and we normalize this data, we need to kind of put a threshold on this data to say whether or not a peak in titanium is associated to a storm or not. And to do that, we looked at 2 historical weather data sets, so the historical weather data set from Canada and the NOAA hurricane data set, and we examined which event happened at the Magdalene Island and which of them had a significant impact that could have caused a significant movement of sediment. And so we found that we should expect in the past century between 3 and 14 events, so quite a big range. So what we decided is to put the threshold for the titanium data such that we identified about seven events per century, which is in the middle of what we would expect to see on the Magdalene Island. And so once you have this threshold, you can extend the threshold to the full record of titanium, and we get our reconstruction. And so this is the same figure, but bigger. So we've got the storm reconstruction for TAC, TLM first, and then the event per century for TAC and TLM as well. And what is nice is that both record, despite being in two different places, they correlate pretty well, not correlate, but they show similar features. Especially we can identify two periods of increased storm activity. The first one was during the last 200 years, where we identified 6 events per century. 6 events per century is about 4 times more than the long-term average of 1.4 events per century. So we're not sure that this increase is actually related to a real increase in storm. It may be related to the industrialization of the Magdalene Island and the building of gravel road, for example, which brought more sediment closer to the peat bog and therefore easier movement of sediment towards the peat bog. So we need to take that into account in the analysis. But the interesting period is between 1450 and 1650 of this era, where we identified 3 events or 2 events per century in both cores. And so when we look at the regional pattern and we compare data to similar reconstruction from the region, we see that at least 4 studies also identify an increase between 1450 and 1650. Here's an example of a study in Saltpond, Massachusetts, where they also identified this period. And from these 4 studies, which are located between the Bahamas and Nova Scotia, so cover quite a big range in the North Atlantic Basin. So from these 2 studies, 2 of them also agree with the first period, the more recent increased period of storm during the last 200 years. And so to come back to my initial research question or goal was to examine what climate context is related to these increase in storm. And this is still an ongoing analysis, but here what we see is the Atlantic multi-decadal variability index. So these positive values indicates that the North Atlantic Basin's water, sea surface water, were warmer than normal, and this surface pressure is lower than normal. So these conditions should be conducive to hurricane formation. So when it's positive, it should be related to more hurricane. When it's negative, it should be related to a quieter activity of tropical cyclones. So what we can see is that the first period here between the last 200 years was indeed related to warm water in the North Atlantic. But interestingly, the second older period happened during the Little Ice Age, where sea surface temperature were quite colder than usual. So we should not expect to see storm in this time. But obviously the picture is possibly much more complex than that, with not just the sea surface temperature, but also the local, not just the average temperature of the global basin, but also local variation, where it's very important because, I mean, cyclone are very local features. So if water is warmer in a certain area, it can have significant impact, even if the whole basin is colder. And as I said, this is being investigated as part of my PhD research, so more to come. And so in conclusion, I can say that the Magdalene Islands are indeed affected by tropical cyclones. So we knew in the recent record it was affected. We didn't know if it was also affected in the past. So now we are more confident that it indeed was affected by cyclones. What's interesting also is that an increase in North Atlantic storm also equals an increase in the Magdalene Island, which we were not sure because the Magdalene Island is located at such the northern latitude, the northern limit of the cyclone track. So we weren't sure if it would be related to all the other cyclone. And finally, so different climate states can be associated with active storm periods, as I just described. So thank you, and any questions?
It seems like we have a question.
So what do you say when asked if cyclone activity in North Atlantic has been increasing and or is likely to increase in the future?
Sorry, what? I didn't hear.
So if someone, okay, so this is, probably what people want to know is cyclone activity going to increase and is going to be more of a hazard in this region going forward? Based on either your research or just your, time thinking about this, what would you say to that question?
I say there's a lot of uncertainty around this. I think the research for now is based on global data of cyclone intensification rate, cyclone frequency. So the data is a bit more clear that with future climate change, we might get more intense cyclone, but we're not sure if we're gonna get more cyclone in general, so a higher frequency. The difficult thing is to say where this is gonna happen. I think it always is when we want to predict climate change. So it's hard to say whether the Magdalene Islands or the Eastern Canada coast will be affected by an increase in climate change in cyclone. But even in the case of Canada, even if there's no strong increase in cyclone, there are other things like an increase in the erosion of the coast, a diminution of the sea ice that protects the coast in the winter that can also affect, give impacts to the same condition of cyclone activity.
Do we have questions online?
Maybe a very quick follow-up. If I understand correctly, you used historical weather data to kind of validate your core data. Could you use? You mentioned insurance industry at one point in your talk. Could you use insurance claim data from that region as a kind of independent validator of the results you're getting? Yeah,
I think that would be a good idea. I think they did that probably in the States where there's a bit more problem with hurricanes in the South. But yeah, that would be, I actually use shipwreck data in part to validate when I saw that there was a storm with strong winds. I went back to the shipwreck record of the Magdalene Island and saw if there were shipwrecks associated with those strong winds, which was a way of validating if there was a visible impact on the Magdalene Island. And I think any type of data that can add to validating, especially back, before the 60s or back in time, is great to have. So insurance claim would definitely be part of this data set.
Thank you, Antoine. If we don't have any other questions, I'd like to thank all the speakers and the audience and online as well to have listened to all of our insightful presentations. And don't hesitate to follow us on the socials and to check the website if you're interested. And yeah, that's it.
All right, everybody, congratulations. Thanks so much for coming in to share your research with us. We did have a largish online audience, but a quietish audience. I'm sure they were taking in all of this information. So thanks for all of you in the Zoom space for joining us as well. We will be closing up the Zoom now, and then we'll be back at 2 p.m. for Climate Jeopardy, the next event for today. So join us back in the same link at 2 p.m. And thanks again, once again. Then thanks once again to Leeds and everybody who's participated today. Bye, everyone.